Look at the new innovation in drone warfare. Ukrainian forces looked at a simple weather balloon and saw a strategic bomber. Reports from May 2026 detail them executing this brilliantly simple tactic. They used a high-altitude aerostat to haul a perennial autonomy Hornet drone 26 miles across the sky, dropping it from an altitude of 26,200 feet. This modest fixed-wing drone, sporting a 6.5-foot wingspan and an 11-pound payload, sipped a mere 5% of its battery during the taxi ride. It arrived at the drop zone retaining a full energy tank. Combining that reserve with the gravitational potential from the drop, the system multiplies the drone's baseline 62 to 93-mile range by a factor of 1.5 to 2. Archimedes figured this out in the bathtub centuries ago. The buoyant force equals the weight of the displaced air. At sea level, dry air density sits at 0.0765 pounds per cubic foot, while helium clocks in at 0.0112 pounds per cubic foot. The difference leaves us with a gross lift of 0.0653 pounds per cubic foot of helium. Subtracting the envelope and rigging mass, engineers aim for 0.05 to 0.062 pounds of useful lift per cubic foot. For the Hornet system, we assume a total suspended mass of 26 to 33 pounds. This includes the drone, the battery, the motor, the guidance, and the 11-pound warhead. Adding a 9 to 18-pound balloon envelope and rigging brings the total lift requirement to 44 to 55 pounds. This demands an initial helium volume of 700 to 1,060 cubic feet at ground level. As the aerostat ascends, the external pressure drops, causing the gas to expand. At 26,200 feet up, the atmosphere changes drastically. Air density plummets to 0.0328 pounds per cubic foot. Pressure drops to 5.16 pounds per square inch, and the temperature freezes at 35 degrees Fahrenheit below zero. The balloon expands by a factor of 3 to 5. The net upward force subtracting aerodynamic drag dictates the ascent rate. Moderate free lift yields ascent rates of 10 to 20 feet per second, putting the balloon at the target altitude in 22 to 45 minutes. During this climb, the balloon drifts with the vector averaged wind. Mid-latitude regions feature average winds of 55 to 67 miles per hour. Sustaining that over 30 minutes pushes the payload 31 to 40 miles horizontally. The balloon merely acts as a passive tourist floating along the atmospheric currents. Releasing the drone gives it two massive advantages. First, it skips the energy-draining climb from the ground. Second, it gains a massive gravitational potential energy bonus. For a 26.5-pound drone at 26,247 feet, the math looks like this. Weight times height equals 26.5 pounds times 26,247 feet, giving us roughly 695,545 foot-pounds of free kinetic energy. In gliding flight, the drone converts this potential energy into forward momentum. Assuming a glide ratio of 10 to 1 from 5 miles up, the theoretical still air glide distance is 50 miles. Factoring in real-world turbulence and drag, a conservative 6 to 1 ratio still provides 31 to 40 miles of gliding range. Once the electromagnetic motor kicks in, the drone has its full battery ready to go. The 5% battery drain during the balloon transit covers the bare minimum avionics draw. Meteorology dictates the launch window. Operators forecast detailed wind profiles days in advance using numerical weather models. They select launch times when the integrated wind vector aligns with the mission geometry. The dominant westerly flow in the region pushes the system eastward, directly toward the intended targets. Some designs incorporate superpressure balloons to change altitude and exploit different wind layers, proving the versatility of the concept. Engineers must choose their lifting gas wisely. Helium provides safe, flame-resistant lift. Hydrogen offers superior lift at a lower cost, bringing along the spicy bonus of turning the whole rig into a spontaneous piñata of fire. Expendable military operations often tolerate the hydrogen fire risk for the performance bump. Polyethylene or composite films make up the envelope materials, enduring freezing temps, ultraviolet exposure, and wind shear. Airspace defenders face a headache trying to intercept these. The 5-mile altitude places the balloon above short-range air defenses. The laughably low cost encourages mass deployment of decoys. Adversaries find themselves wasting premium interceptor missiles on empty party balloons, a strategy sure to give defense contractors a delightful heart palpitation. Once released, the drone dives rapidly, minimizing its exposure time. The overall viability remains ironclad. The approach relies entirely on standard aerostatic engineering, bypassing exotic materials and propulsion miracles. Mass-producing these systems is incredibly cheap, with the drone and warhead making up the bulk of the cost. The balloon and gas add mere pennies to the spreadsheet. Ukraine's reported test showcases a brilliant manipulation of buoyancy, energy conservation, and atmospheric wind fields. They turned the atmosphere itself into a delivery vehicle, multiplying the reach of a low-cost drone by dusting off centuries-old ballooning science and bolting it to modern aeronautics. As we observe these events unfolding in May 2026, the battlefield reports present a plausible emerging tactic, while the math and physics remain verified fact.